Okay. So we were working on the matrices stuff last week or whenever we were last working on stuff. So now we're just going to do some more stuff with it. Before we did like add, subtract, and multiply. Now what we're going to do is we're going to take some of that stuff that we've figured out, like with the add and subtract and multiply, and use it for certain purposes like size change, rotation, reflections, that kind of thing. So the first one we're going to do is size change. So if you remember back from geometry, size change is basically when you're taking a shape and you're either making it bigger or smaller. Does anyone remember how we go about making it bigger or smaller? So what you end up doing, and it kind of says there, so like for any k not equal to 0, the transformation that maps, you just got your normal xy there onto kx and then ky. Basically, whatever that k value is, they tell you you're doing a size change of, you just take your coordinates and multiply it by that number, okay? So like if it was a size change of 2, you just take all your ordered pairs times 2, basically. And then it says there with center 0, 0, so it's just expanding off 0, 0, magnitude is k. And then they denote it there as that S sub K. So whatever this sub letter is, that capital S just stands for size change. The little K there tells you like how much bigger or smaller it's getting. Do you guys remember how to make it smaller? Like what kind of number we'd multiply to make it smaller? Not negatives. Negatives actually do a flip. Decimal numbers. So like if you had like 0.5, that would make it half as big. So if you have decimal numbers, it actually makes your shape smaller. If it's, just positive numbers like 5 or something like that, then it would make it 5 times as big. So then there is that size change theorem there that has that S sub k again. And then this is the matrix we would use to multiply by if we needed to do a size change of whatever that number was. So like if it was like S sub 5, you would just put a 5 into those spots. You don't want to put a 5 in, or whatever your value is, into all of the spots, because how it works with the multiplying is, remember how you take everything in this row times everything in like the columns going the other way. You just have to multiply once. You don't have to multiply everything by whatever that value is twice. And you can kind of see that a little bit here with the identity matrix. So identity matrix, basically, if you type this in like 1001 times whatever, it's going to kick out the same exact thing as what you started with, because those are both ones there. So like if you did a size change of 1, is that going to change its size at all? No, because multiplying by 1 just keeps everything the same. So that's called the identity matrix, where whatever you multiply it by just kicks out the same thing. But you can kind of see here how, like, this would be our size change number times the x coordinate, but then we wouldn't want anything times the y coordinate for our top point, so that's why it's 0 there. And then for our second row, it's 0 for the x coordinate because we don't want anything for the x coordinate, but we want that y coordinate to be whatever. So then it kind of shows there. So that's why there's those zeros in there. But yeah, so that's the size change matrix. Distance formula we're going to need, so it's kind of similar to like the Pythagorean theorem type, where it's, like a squared plus b squared equals c squared, but then they solve it out where it's just the square root there. Realistically, I don't think you really need the absolute values and the squareds, because the point of the absolute values or the squares is to get rid of negative numbers, because can we ever have negative distances? No, it's not like I'm driving negative 5 miles to Stanwood, right? So we can't ever have negatives there. So that's why it has absolute values in the square root. Like I said, I don't think you really need both of those. I think you could also go with parentheses there, and then squared plus parentheses and squared, but that's the way the book had it, so that's why I wrote it. But basically, you just take your 2 x coordinates and subtract them, square that. Take your 2 y coordinates and subtract them, square that. Add those together, square root it, okay? And that will always give you your distance between 2 points. And then just a review on some of the size change properties, very similar to what we learned in geometry. They're going to be similar to each other, so like they're going to be different sizes, but the shape's going to look the same. Like if it started as a smiley face and we did a size change of it, it's going to stay as a smiley face. Corresponding angles are congruent, so if you got a 90-degree angle on one shape, you go and do a size change, it's going to still stay at 90. And then the ratio of the corresponding segments is equal to k, and we'll do an example with that in a little bit here. Okay, so the rest should be on our example sheets. So the first one here, it says, given PIE as a triangle with P at negative 2, 0, I 2, 0, and then E 0, 3, find the image of the prime version of that under size change 6 using matrices. So because it says specifically using matrices there, we're going to set it up with our size change matrix. if it was just a size thing, change thing in general, and it didn't say that, I don't care if you use the size changer matrix or not. But because it wants us specifically to use them, we'll use that size change matrix. So we'll take that one from up here that we had with the k and the 0 in there, but instead of that, our k value is 6, so we're just going to go our bracket there, 6, 0, 0, 6. And then we're just going to take our size change matrix times whatever our original ordered pairs were, so like P, I, E. Remembering when we do these, it's always the x coordinate on the top and the y on the bottom. So for like P, it's like negative 2, 0, I, 2, 0, E, 0, 3. And then when we kick out an answer, it should be the prime version of all those points, okay? So like I said, size change isn't too bad if you want to do it by hand, but because this is matrices, I'll just remind you how to do it on the calculator. So if I was going to do this on the calculator, what I would do is I would go second, matrix, and then we want to arrow over to edit because we want to edit our two matrices. And then I need to change my first one to a 2 by 2. So once I get over to edit, let me skip some steps to get over to edit. I'm going to type it into my first one there into A, change it to a 2 by 2. Type in my stuff here. And then once I get that typed in, you want to go second quit to get out of that. Then second matrix again, over to edit, and then you type in your one for your shape there. So I'm going to go down to B to type this one. This should be a 2 by 3. And then type that in. And then again, as you're doing that, you want to hit second quit to get out of all of that completely. And then to actually multiply them, you just go second matrix. We're taking our first one to A times our second one to B, so you just stay on names because we're just selecting the two matrices. So enter, and then just times, and then go down to select your second one to B, enter on that, enter again, and it should give you your new matrix there with your ordered pairs. So it would be negative 12, 0, 12, 0, 0, 18. And like I said, with the size change stuff, you could also do it by hand because basically you're just taking each one of those ordered pairs times 6. So like 6 times negative 2 kicks out the negative 12. 6 times 0 kicks out the 0, and so on there. But because it says using matrices, you'll just want to make sure you show that. And then graph the pre-image and the image. Probably wouldn't hurt here to change this to counting by 2s because this is going to go all the way up to 18, and our graph here is only going to go up to 10. So I'm just going to change these here. Instead of going by those numbers, I'm just going to write like count by 2. And I'm just going to keep it consistent going both ways just because. So just change both of those to count by 2 just because these get into really big numbers. So my original one there would be negative 2, 0. So if I'm counting by 2s, really I'm just going over one space. That's P. I 2, 0, so over 2, up 0, and again it's just over one space because we're counting by 2s. And then 0, 3, over 0, up 3, so that'd be like at 1.5. That's I and E. It's a triangle, so you want to connect all those sides there. And then graph the other one. So our other one there, prime one, we got negative 12, 0, so that would be out to like the negative 6, counting by 2s. And that would be our P prime. 12, 0. I prime. And then 0, 18, so that'd be up to the 9. For E prime. And then obviously you can see there, it's the same type of triangle, you know, similar where those two sides are the same and that kind of thing. Just obviously got 6 times as big. And then it says, are they similar to each other? Well, what do we think? Are those shapes similar? Yeah, they would be. So that means they're proportionally the same. So yes, the pre-image and image are similar or something like that. And then just a reminder, pre-image is the first one before you do any movements, and then image is your new one after you do all your movements. Alright, ready for the next one? Okay, so then the next one here, we actually have to use our ordered pairs from that first one there. So our ordered pairs from the first one, just going to write them down here so I got it. Okay, so P was -2, 0, I 2, 0, E 0, 3, and then our prime ones was -12, 0, 12, 0, and 0, 18. Okay. So then what it wants us to do is it wants to find a bunch of distances here. So remember when it's like two letters just next to each other like that, that means distance. So they want us to calculate the distance from P prime to I prime, and then divide that by the distance P to I. Okay, so we're going to find a lot of little distances here. So we're going to want to use our distance formula. So that was the one from the previous page where it was big square root there, your x, I think they do x2 minus x1 squared plus y2 minus y1 squared. The order of those isn't super important because you're going to end up subtracting them and then squaring them anyway, so the order doesn't really matter. But so like for the first one there, for p prime, I prime, we're going to take our p and our I and subtract those. So it would be, so for p prime, I prime, it would be -12 minus 12 for x is squared, plus, and our two y values are 0 and 0, so 0 minus 0 squared. So then when we solve that out, -12 minus 12 would be -24, right? Squared, that's just going to be 0 squared, which we know really is just going to be 0, right? So then we'll have -24 squared, which I don't know off the top of my head. 576. And then obviously we'd add that to our 0, but obviously then it's just still the same thing. And then realistically, if we had that number and then we squared it to get that, and then now we're at this number and we square root it, what's it going to go back to? 24, right? So our distance from P prime to I prime would be 24. And then we're going to do that over our distance from the P to the I. So P, I, distance formula there. So that is going from -2 minus 2 squared plus 0 minus 0 squared for our order pairs. -2 minus 2 would be -4 squared. Other side is just going to be 0 squared. And then again, the 0 is kind of convenient on that. It's just going to cancel out. -4 squared would be 16. And then square root of 16 would get us back to 4. So pi would be 4. So then when we set up our fraction for that, it would be p prime I prime, that distance, over pi, that distance. So p prime I prime was 24. Pi distance was 4, and what's 24 divided by 4? 6. So that's the first one. Yeah, and then we just do it with the other ones. And realistically, some of these aren't too bad to calculate. Like that one, you probably actually could have just counted by hand because it was on a straight horizontal line there. So like it's 12 to there and 12 to there, so it's going to be 24. The other ones, though, these are going to be diagonal, so they'll be a little harder to calculate. So here we will have, so what's our next one? PE. So P prime to E prime. Giant square root there. P is at -12, 0, so it'd be -12 minus, and then our other x coordinate for E prime is 0 squared plus, and then our y coordinates, it would be 0 minus 18 squared. So that would be -12 squared plus -18 squared. -12 squared would be 144 plus, I don't know, 18 squared off the top of my head, 324. And then we would have to add those together before we square root them. So you would do 324 plus 144, which is 468. And then if you square root that number, it's going to be a gross number. Instead of rounding, I'm just going to keep it as this square root for now, because in the end we're going to end up dividing, and if you round, your answer's not going to be accurate. So I'm just going to leave it as that square root right now for that distance. Then I'm going to find my distance between the p and the e, just normal numbers, or the original ones. So p, so we'll have square root -2 minus our other x coordinate is 0 squared plus our y coordinates, so 0 minus 3 squared. So that would be -2 squared plus -3 squared, which would be square root of 4 plus 9. And then 4 plus 9 would be 13, so square root of 13. And again, that's not going to come out nice either, so I'm just going to keep those as is. Because then actually when I do this out here, it's kind of an interesting thing. So if I go p prime, e prime, divided by p, e, I would have the square root of 468 on the top, square root of 13 on the bottom. And then if you actually do those out, so if you do square root of 468 divided by square root of 13, it actually comes out to be a perfect 6. Okay, so that's why we don't want to round on that, because if you round, your number's not going to come out exactly 6, but it should always come out to be exactly what your magnitude was. So that'll actually come out to be an even 6. And then one more time here. So we got to go I prime, e prime. So we'll go square root of, it would be 12 minus 0 squared plus 0 minus 18 squared. So then that would be square root of 12 squared plus -18 squared. And conveniently, we had 12 and 18 before, right? So it was 144 plus 324, which ended up being square root of 468. So the numbers end up being the same just because the distance, it's an isosceles triangle, so the distances are going to be the same. So again, we'll keep that as that square root because that's kind of a gross number. And then we'll go I to e, which is square root 2 minus 0 squared plus 0 minus 3 squared. And again, we should have similar results here where it should be 2 squared plus -3 squared, so square root of 4 plus 9, square root of 13 again. And then again, we'll keep it exactly as that. So we'll go I prime, e prime, divided by I, e, which would be square root of 468 divided by square root of 13, which again is just what we had on our calculator, so that'll also kick out a 6. Okay, but it should always, the ratio should always come out to be the same thing as your size change value. It's kind of a lot doing all that distance formula stuff out, but that's just distance formula. Okay, so that's it. So you got the rest of the time to work on that book page assignment there, 246, 1 to 17, but skip number 16. Okay?